Hey, my name is Dan Oake, and I'm a student at Athabasca University, and I'm currently taking the course Computer Science 444, Embedded/Robotic Programming. And I've been doing a couple videos going through the SparkFun Inventors Kit Guide, which is associated with the Comp 444 course, as well as you get the SparkFun Inventors Kit that comes with a lot of cool things. And I'm basically going over how to do Project 1, which is very well laid out in the SparkFun Inventors Guide, but I'm just basically showing a fellow student in Comp 444 doing Project 1 and the 4 circuits associated with it, Circuit 1A, 1B, 1C, and 1D. In the previous videos, I've went through Circuit 1A and the coding challenge associated with it, and Circuit 1B and the coding challenge associated with it, and now I'm going to attempt to go through 1C and 1D. So we last left off finishing the coding challenge for Circuit 1B, which was using a potentiometer to control the blink rate of LEDs. And the code is still up on this circuit board here, showing that the LEDs are all blinking at a different rate based on the potentiometer. So the red LED is blinking at a rate 2 times that of the pot position, and I believe it's all the way up at 1024 would be the pot value. So this is blinking at about a rate of 2046 milliseconds, so about 2 seconds. The blue LED is about half of the pot value at about 512, which is about half a second, and the green LED is blinking at about a third of the original value, so around 750. So that explains the blink rate there. That was in the previous video. If you ran into any issues during that video, the troubleshooting would be this. The potentiometer you should read in a value between 0 and 1023, which corresponds to 0 volts and 5 volts. If you are not getting values like that and you're not getting what you expect, it's quite possibly that you misaligned the actual wire from the pot pin. And the reason being is it's very easy in real life to mix these up. So for example, in this potentiometer, one of the pins gets connected to ground, the other terminal pin gets connected to 5 volts, and then on the other side the pin would get connected to the analog input. But I mean, it'd be very easy to misalign these pins and have the wire off to the side. So check your actual physical wiring. That's going to be the case a lot of times with electronics. The wiring is going to be a problem more than the coding. If you're not getting any values or getting random characters in the serial monitor, make sure that you have the correct baud rate on and that you're on the correct serial port. So I showed in the previous thing that if your serial monitor has a different, like right now I'm reading on the serial monitor values. So I'm reading different values on the serial monitor because my baud rate is set at 9600 and in the code it's 9600. But if I had the baud rate, the code at 9600 and the baud rate in the serial monitor, it's something different, I'm going to get weird characters or I'm not going to read values. So you need to make sure that those values match. And make sure that you have the correct serial port connected. So when you have your port, make sure you're on the correct serial port. That's a couple of the troubleshooting things you might have ran into. And so, like I said, we've already completed Circuit 1A, blinking an LED, and Circuit B, where we are reading a potentiometer value. Now we're going to move on to Photoresistor, dealing with those. So in Circuit 1C, we're dealing with photoresistors, which changes a photoresistor changes its resistance based on how much light the sensor receives. Basically, it's how simple nightlight works. The components we're going to need: an LED, a photoresistor, 330 ohm resistor, and a 10K resistor, so 10 kilo ohm, and a bunch of jumper wires. I'm going to go a little faster through this because my videos are incredibly long, so let's see if we can do this. Photoresistors are light-sensitive variable resistors. The resistance of this component changes depending on the amount of light that is on this part here. So the more light that shines on the sensor's head, the resistance between its two terminals decreases. So more light actually causes the resistance value to go down. So the resistance goes up in darkness. So they're kind of like a darkness sensor more than a light sensor. But so again, this component is required for ambient light sensing. The new concepts we're going to talk about is analog to digital conversion. We've already talked about what analog was and what digital was. Analog being, what the real world's based on, so reading a spectrum of values. And digital being finite, discrete values, like on, off, high, low, and 0, 1, that sort of thing. So the red board, which is our Arduino board that we're using from SparkFun, will sense the analog signals, and then it passes them through an analog to digital converter, an ADC. So there's 6 analog inputs, A0 through A5. We discussed this in the previous videos, and they all use ADCs, analog digital conversion. And basically they convert that infinite, range of values, which is the analog world, and we actually do put them into discrete finite values. But they're not digital. We put them in more than 2 values, more than on and off, but a certain number of values. To be specific, we have 10-bit resolution, so the resolution of this signal, this ADC that we have on this board, and various Arduino boards, is a resolution of 2 to the 10th power, which is 1024 possible values, which is why when we were reading it on the potentiometer, if you watched the previous video, we could have a value from 0 to 1023. So 0 was one of the values, and then up to 1023, that represented 1024 distinct values. So again, the resolution of this signal is based on the resolution of the ADC, the analog digital conversion. In the case of the red board and my Elegoo board that I'm using, and a lot of the other Arduino compatible boards, the resolution is 10-bit. So with a 10-bit ADC, we get 2 to the 10 power values, which is 1024 possible values. Why is it 2 to the 10? Well, 2 because we're dealing in binary, which has 2 different values, 0 and 1. And then when we raise that to the power 10, this is what we get, which is why the analog signal can vary between 1000 and 23. Voltage dividers continue. We talked about voltage dividers in the previous video about how a potentiometer really allows us to create a variable voltage divider. And a voltage divider is basically using 2 resistors to take in some input voltage and output a smaller voltage based on the 2 resistor values. And if you use the potentiometer as one of those resistors, you can create a variable voltage divider where you can change the output voltage. Now, since the red board can't directly interpret resistance, rather it actually reads voltage, that's what the analog inputs do, we use a voltage divider in order to use our photoresistor. The voltage divider equation is as follows. So the voltage out, what we actually read in, equals the voltage in times the ratio of resistor 2 divided by the sum of resistor 1 and resistor 2. So this assumes that you know the 3 values of the above circuit. So we need to know these values. The input voltage, Vn, and both resistor values, R1 and R2. So if R1 is a constant value, so let's say it's the resistor in our circuit, and R2 fluctuates, it's the photoresistor, which again has a variable resistance based on the ambient light level, then the amount of voltage measured on the V out pin will also fluctuate. So let's look at the circuit and then we'll solidify that concept a little more. So as usual, we have a single LED hooked in on our breadboard, and the negative terminal or the negative leg is connected to the ground or the negative bar of our breadboard, which is ultimately connected to our ground of our microcontroller. And the positive leg of the LED is connected through a resistor, in this case a 330 ohm resistor, based on the color band of red, red, brown, and then it's connected to digital pin 13. Obviously, as well, the positive rail of this breadboard is connected to the 5 volts of the Arduino or the red board. And then here's our voltage divider circuit. So again, we've got one end of the resistor connected to ground, and then one end of this variable resistor, this photoresistor, connected to positive volts, and then the middle, the other end of both the resistor and the photoresistor are connected together, and that's connected to analog pin A0. And this is very similar to how a pot works, in the sense that we had 3 pins on the potentiometer, an external pin which was connected to ground, the other external pin was connected to 5 volts, and the middle pin, the wiper, was connected to our analog input. And we said that by turning the knob internally, you basically had a wiper that basically divided the internal resistor at whatever ratio. So if you had it in half, you divided it in half. If you had it at one end, you got the full resistance. If you divide it, if you turn the knob to the other end, you got none of the resistance. So this is essentially, in some sense, kind of a potentiometer setup, or voltage divider setup. But instead of turning a knob to be able to control it, we're going to have the resistance of this change based on the value, which will output a different voltage here. Well, a different resistance, which we read as voltage. So basically, this circuit we have it connected to ground, and then 5 volts here. So 5 volts potentially could run through this circuit, but what we pull off is going to be anywhere between 0 volts and 5 volts, depending on how the voltage divider circuit works out. I'm going to give an example here too. I'm just going to sidetrack. I know I promised to make these videos quicker, but I'm going to try to do a quick sidetrack here. With how the voltage divider equation works out. So if V out, as the voltage divider circuit works, we have V out equals V in times R2 over the sum of R1 plus R2. So, and in our circuit, V in is going to be 5 volts. So V in is 5 volts because that's what we're getting from the microcontroller. V out is what we're going to read in. V out is the voltage coming out of that where the pin of the resistor and the photoresistor connect, so that middle section, and this is what's going to ultimately be read in to analog pin A0. R2 according to, again, our we're saying that if R1 is a constant value, so if R1 is the resistor and R2 is the photoresistor that fluctuates, well, in this case, R2 is the photoresistor, which we know fluctuates, and R1 is 10 kilo ohms. It's a 10 kilo ohm resistor because that's what we were told to use. Well, then we would go like this. We're going to go V out equals 5 volts times R2, which we don't know the value of yet, but let's say if it was, 10 kilo ohms. Let's say it ends up being a 10 kilo ohm resistance based on the ambient light level. 10 kilo ohms. And then we already know R1 is 10 kilo ohms, so then 10 kilo ohms plus 10 kilo ohms, so R1 plus R2. Then V out is going to equal 5 volts times 10 kilo ohms over 20 kilo ohms, which equals half, right? So it equals 5 volts times half, and the kilo ohms cancel out. And 5 volts times half means that V out equals 2.5 volts. So if our photoresistor ends up having the right amount of ambient light on it to make it essentially a 10 kilo ohm resistor, then we would end up basically creating a voltage divider that outputs half of the original input voltage, and because the microcontroller is giving us 5 volts, we would output 250, and that's what we would that's what we would read into our analog pin A0. Now, if we suddenly had a lot less resistance, so again, we know that in lots of light, the photoresistor actually has very little resistance. So let's say if we drop that to, if we do our V out equals 5 volts times, say if that had very little resistance, let's say, 100 ohms over 100 ohms plus 10 kilo ohms, because this is the sum of R1 and R2, but if R2 is 100 ohms because it's got very little resistance because it's in a lot of light, then I don't even have a calculator with me, but basically we're going to have a very small value. This value in the numerator is very small compared to the denominator. So we're going to have 5 volts times 1 over 1100, or 100 rather over 1100, right? Which is, for my ease of math, is just going to be 1/11. And that's going to make that 5/11, which is approximately, 11 doesn't go into 5 at all, right? So this is approximately half. I'm just going to say that's approximately half a volt for simple math. So a lot less voltage is going to be read into A0, which means, say if we're using that to, light up an LED, well, the LED is not going to be very bright. Whereas when we had 10 kilo ohms of resistance, meaning it was getting darker or dimmer, we had 2.5 volts going through, meaning lighting up. And if it got really dark, let's say if this went up to 20 kilo ohms, well, if we had 20 kilo ohms over 20 plus 10, 30 kilo ohms, which is 2/3 times the 5 volts, 2/3 of 5 volts is 3 point something, 3.7 volts. So we have a lot more voltage. This is really messy, and actually it's hard for me to follow, but basically in high light conditions there's very little resistance that the photoresistor gives us, so we're going to have very little output voltage, meaning if we're using that voltage to, say, power an LED, it's going to be very dim or not on at all, depending on what threshold we need to get over. And if it's really dark, we're going to have a lot more resistance in the photoresistor, meaning we're going to output more voltage. But that's basically the circuit. I promised to start making these quicker, so let's just get to it. The program is going to store the light level in a variable called photoresistor. If the photoresistor value is above some threshold, we're going to say it's bright, and we're going to turn the LED off, and we're going to decide on the threshold. And that's going to change based on the ambient light in the room. You might have to set that. Otherwise, if the photoresistor is below that threshold, that means it's dark in the room, and we're going to turn the LED on. So let's get right to the code. So this is the photoresistor LED code, and again, I got this right from SparkFun. First things first, we're going to upload this and get rid of the old program that's currently on there. And this circuit is no longer the one we're concerned with. This is the circuit I have done up with the... I'm going to unplug this just for a second so that LED doesn't go off. This is the circuit now that I have done up with the resistor. So one end of the resistor is tied to ground. One end of this photoresistor is tied through that red wire to the power rail, and then off of the middle pin, so where both the resistor and photoresistor are connected, I have this yellow wire which connects all the way back into analog pin A1. So that yellow wire goes all the way back into analog pin A1. This other yellow wire is to the other part of the circuit, which is the potentiometer. And this blue LED, which one end is connected of this LED, is the negative end is connected to ground, and the other end goes through a resistor and then goes through this blue wire, which is connected into pin A2. And it's really dark because I seem to have lost power to this light, so see if we can get that going. If not, okay. So no light, but hopefully you can still see the circuit there. And again, I've got the blue LED hooked into pin A2. Now, I've got it hooked into pin A2. It's one of the analog pins, and it really should be a digital pin. But because I've got so much stuff hooked up in this one Arduino, I've kind of lost my digital pins. But the cool thing is you can use analog pins as a digital pin if need be. So by default, they're set up as analog pins, which is why when you call the pin mode, you don't actually have to declare them in pin mode because they're analog, they're input by default. So you don't have to say, hey, pin A0 and A1 input. But because I'm using it as a digital pin, I do have to declare pin A2 as an output. So analog pins are cool in that way that if you run out of digital pins and you need another digital pin more than you need an analog pin, just hijack an analog pin, as I've done. So again, you're really just focused on this top part of the circuit. This is the photoresistor that's now no longer connected. And let's plug this in. Okay. So now what we're reading on the serial monitor is the value, I believe it's the threshold. Let's take a look. So this is the code that, again, you can get down from the SparkFun Inventors Kit website. Basically, it's got a couple of variables, one for the photoresistor, which is set to 0 by default, and then one for the threshold, which is 650. Basically, if the photoresistor reading is below this value, then the light will turn on. So that's just a value you kind of set based on the room level. So right now, for example, we're printing to the screen the photoresistor, the value we're reading in off the photoresistor, like off that voltage divider circuit. And we're reading around 750. So that's why we have the threshold at 650, because we don't want it turning on. If the threshold was at 750, I'll just show you, the LED would be on all the time. So let's just re-upload that, and you'll see this blue LED come on all the time because I've adjusted the threshold to the amount that's already in the room right now, based on how dark this area is on my desk. And you can see it's flashing on and off. Why? Because sometimes we're going below 750 at 740, 743, 55, and it's flashing on and off uncontrollably. So we'll lower that to something like 650, or maybe even 600. And that way we won't, have this effect going on during the video. So those are the two values, the photoresistor value, which is what we're going to use to read in off that voltage divider made up of a resistor and a photoresistor, and a threshold, which is just something we're deciding we want the LED to turn on if what we read in here off of our voltage divider goes below that amount. In setup, we set up our serial communication as normal, and then we set up pin A2 as an output. Again, we didn't have to set up our voltage divider pin, which is A1 in this case, as an input because the analog pins are input by default. However, normally we would have used the LED off of a digital pin, and we would have set that as an output as regular. But in this case, I ran out of digital pins, so I'm using A2 as a digital pin. So because I'm using A2 as a digital pin, I do have to call the pin mode function on it and set up A2 as an output. Again, I could have used a constant for A2 and actually set this up as LED pin up here with a hashtag define or something like that. LED pin A2, and then could have used it down here directly. So LED pin, and that's a little more explicit about what's happening, but in either case the code will work. It's just one's more readable. In the loop, all we're going to do is we're going to read the brightness of the ambient light. So we're going to do an analog read off of A1 and assign that to photoresistor, our int variable. So again, we're going to set the photoresistor to a number between 0 and 1023 based on how bright the ambient light is. Now again, in this particular case, we see we're reading in a value around 750. And then we're going to print that value to the serial monitor, which is what's happening here. If the photoresistor value is below the threshold, we're going to turn the LED on. Otherwise, we're going to turn it off. So basically, if it gets dark enough in the room, we're going to read in a small enough value, because again, the resistance of this thing goes up as it gets darker and as the resistance goes up, we're dropping more voltage here and we're not going to read as much in. So we're not going to have as much to output, and therefore we're going to eventually drop below the threshold and turn on the LED light. So again, if the photoresistor, which is this value here, is less than the threshold, which is a value we set up here, right now it's at 600, if that's true, we're going to call digital write on A2 high. So again, even though this is an analog pin, we're calling the digital write function on it, on pin A2, and we're just going to set pin A2 high. So we're going to turn the LED on, else we're going to turn the LED off by going A2 low. So this is an if-else statement, so only one of them can be true. Either the LED pin is going to be on, because we're sending a high signal to A2, or it's going to be off. And then we're going to have a short delay of 100 milliseconds just so that we can read the printout. The delay is not for the LED. That can happen instantaneously. The delay is so that, we can actually read the numbers. If there was no delay, it'd just be too hard to even discern. And that's pretty much how simple that code is. So again, if we make it darker by covering up the photoresistor, the LED comes on. So LED is on when it's dark because I'm covering the photoresistor, and it turns off when it becomes light. And again, you can change the threshold to suit, maybe you want to come in on earlier, like do you want to come in on here, or maybe you don't want it coming on until like I'm fully covered, until it's really dark. So we could always go in and adjust that value to 200. And you'll see it might not come on until I'm a lot closer to the to having my finger directly over the photoresistor. So again, here I have my hand over it. It's dark, but you can see the reading on the serial monitor over there in the lower left corner of the screen is still 500 and some. Still 500 and some. You can see the light's not turning on. My 400 and some, 300, still 400, into the 300s now. The LED is still not coming on. I pretty much have to get right on it to turn it on. So I pretty much have to put my finger on, I have to put my finger on the thing, and even then actually when my finger's covering it, it's only at 200 and some, so it doesn't always come on. So we realized that threshold is too low. So I'd have to adjust it, and that's basically what you're going to do. In your coding, you're going to know the environment this is in, the light, the area it's in, maybe it's in a bedroom, if there's, what the light situation is in that room at night and when you want it coming on, based on whatever reason. Your kid doesn't like to sleep in the dark, or you want to be able to see walking down the stairs. And then when you set the threshold appropriately, it's going to turn on. It's got this weird thing because I've got the threshold so low and it doesn't want to read it that low, so it keeps jumping. But in which case you realize, okay, that's way too low, so let's make that 550. And that's basically what you do. You'd set the threshold to match. But again, you've created a voltage divider here with a constant resistor value and a variable resistor that the resistance varies based on the light level. And depending on what you're going to read in on the analog pin, you're going to turn on that light or not. So as it gets dark, you turn on the light. And that's essentially what you're going to do. Now that is the regular code for this, which I'm just going to X out of. So that's the regular code. But as usual, there's a coding challenge associated with this. So we'll get to that. So with the coding challenge, I'll quickly show you what the coding challenge is. First, this is the code to note associated with just the regular thing we just did. Basically, we used if-else statements to control the logic. If some logical statement was true, then we're going to run some code. Else we're going to run some other code. This is basically how we decided when to turn on the LED versus not turning it on. We also dealt with some logical operators, less than and greater than, that sort of thing, but we only used the less than. We basically said if the photoresistor value is less than some threshold, do something. So the logical operators, we have less than, greater than, less than equal to, greater than equal to, equals equals, all that stuff is in the thing. The coding challenge, what is the coding challenge? Okay, right now your if statement turns the LED on if it gets dark, but you can also use the light sensor like a no touch button. Basically, if you have someone going towards a button to touch it, like your kid, and you don't want them to touch the big red button, you could have, some alarm or something go off to say don't touch this, or at least alert you that your kid is going to touch it. So we're going to try using digital write and delay to make the LED blink a pattern when the light level drops. And then we're going to calibrate the threshold variable in the code so that the blink pattern triggers when you wave your hand over the sensor. So when you wave your hand, we'll trigger it. Also, we were also going to replace the 10 kilo ohm resistor with an LED and alter the circuit by replacing that resistor with an LED. The negative leg should connect to ground, obviously, and we're going to see what happens when you place your finger over the photoresistor. Basically, just a great way to see how Ohm's law works, and basically how the voltage divider is truly working. Now, I didn't quite do the coding challenge the way this says, just blinking a pattern. I kind of did something a little more interesting, I thought. So we'll see that right now. So again, you're still looking at this area, but let's see what I did. So again, I've done some doxygen comments, hence the / asterisk. This extra asterisk there basically makes this a doxygen comment instead of just a regular multi-line comment. So I've got these little tags like @file, this is the name of the code, the file, @brief description of what this program does. Program to blink an LED and play a tone based upon ambient light levels using a photoresistor. So I am going to play a tone. This program uses a photoresistor to detect changes in ambient light. When the light level drops below a specified threshold, an LED blinks and a piezo buzzer plays a sound pattern. The buzzer's volume can be adjusted using pulse width modulation. I think I actually took that out just because I was trying to simplify the code. So I'll take that out here. And then I have @author, Dan Oake, my student number. Probably shouldn't have it there. And then the date that I originally made this code. So it's been a little bit, a couple days, the weekend and, kid stuff. And then I've created a bunch of constants here. So again, just a constant associated with my LED pin, which is A2, my photoresistor pin, A1. So both analog pins, although I'm using A2 as, an output pin. My buzzer is on pin 3 because it has to be on a, I guess in this case it doesn't, but I have it on a A3, a pulse width modulation pin. My threshold is 250, so that's the light threshold to trigger or blink the LED pattern. Again, you can adjust this just as I did a minute ago. And the blink delay, I have it set up as 200, so 1/5 of a second, because again, this is a blink delay in milliseconds, so 200 milliseconds is 1/5 of a second. So those are all constants, and I've used the const keyword as opposed to making these hashtag define values. But again, just a style, you can choose to do either or. I've created a variable, light level. Now, why did I create this as a variable and not a constant? Well, because this is going to be changing. This is going to vary. So int light level, I initially set it to 0, and this basically stores the current light level. This stores the current light level associated with the photoresistor. So I had named this photoresistor, or it was named photoresistor by SparkFun in the previous code. I just called it light level because, that's what it is. It's reading the light level, which is based off the photoresistor. These little things, by the way, this little 3 / in this, you can just ignore that. That's again all associated with the doxygen comments. These are essentially inline doxygen comments, the way this is a multi-line doxygen comment. Again, that's just special comments that allow me to automatically generate HTML files based off of the code, which is beyond the scope of this video. And all these comments, so for that matter, you can just ignore. They're all just those special comments that I've created. But they do tell us what the program does. So in this case, setup configures pin modes for LED and buzzer and initializes serial communication for debugging purposes. So again, as usual, set up your serial, set up your pin modes. LEDs, no put pin, buzzers, no put pin, because we're going to be sending the tone to that buzzer. In the loop, we're going to constantly be reading whatever the light level is by doing an analog read of the photoresistor pin, just as we did in the previous code. And we're going to print that light level to the serial monitor, just as we did in the previous code. The only difference is I'm calling the variable light level and not photoresistor. If the light level is below a threshold, we're going to blink and play a pattern. So just like before, we were verifying if the light level is below a threshold, and we just turn on an LED. Now we're going to blink the LED and play some pattern. Else, if the light level is not below a threshold, meaning it's still bright out, or there's still light in the room, we're going to have the LED off by calling digital write to the LED pin and setting it low, and we're going to call the no tone function to the buzzer pin, meaning we're not going to have the LED on, it's going to be off, and we're going to have no sound. And then again, we still have the short delay in the code just for readability of the serial monitor. But all the magic is happening in this function I've created called blink and play pattern. And what does it do? Well, let's read the thing at brief. It's a function to blink the LED and play a tone pattern. This function uses digital write for the LED and tone function for the buzzer to create a synchronized blink and sound pattern. So void blink and play pattern, I'm using a for loop to go from 0 up to 3. So this is going to iterate 3 times. So it's going to blink and play 3 times. It's going to turn on the LED by sending a high signal using digital write to the LED pin. And then I'm going to play a tone at 1000 hertz. So the tone function, if you're not familiar, basically takes in 3 arguments. The first one being the pin that you have your buzzer hooked up to. So in my case it's pin 3, but it's denoted by this buzzer pin constant. The second one is the frequency that you want to play on the pin, that you want to play on the speaker. So I've got a frequency of 1000 hertz. And then how long you want to play that sound. So based on the blink delay. I'm playing it for 200 milliseconds because that's what blink delay is. And then finally, I do the blink delay, so I pause the code for a certain amount of time. This is more associated with the LED. And then I turn the LED off. I call the no tone function, so no tone buzzer pin, and then I delay. So in this function, I actually don't need to put this blink delay. This technically tone function will play the tone it'll send a tone of 1000 hertz on buzzer pin for whatever blink delay is, so 200 milliseconds, and then stop. But I could have also just omitted this third argument and just basically output 1000 hertz to buzzer pin indefinitely, and then when the no tone got called, it would just stop it anyway. So this third argument is really redundant, but I have it there explicitly just to really drive home what I'm doing, I guess. And then I delay again. So all this code does is turns on and off an LED for a certain amount of time that I've decided based on blink delay, and I play a tone at the same time as blinking the LED, and the tone is 1000 hertz. So without further ado, let's upload that to the board, which I think I already did, but let's do it again. And we'll get the serial monitor going again. I've decided I wouldn't have made it as a YouTube personality because my videos are incredibly long and all over the place. Okay. So currently this is the light level in the room. Now it's set up to, again, it's a no touch button. So some kid's going to press the red button and they're hovering over that button to make it dark enough. The LED should blink a pattern and the sound should happen. Let's see if that happens. So again, I got over it. So I went to press the button, the LED blinked 3 times, and the sound went again. So again, I'm going to press the button. Oh. I keep pulling out the wiring. So again, make sure, I've got a lot of wires pulling on each other here, not that great. I've tried to do a bunch of stuff all at once, so I didn't have to make the circuits in between, but you know, I'm pulling wires here, and again, if you have any issues with your circuit, it's often going to be the wiring here. Something came out if you're doing it improperly like I'm doing here. But again, get everything back, and have your no touch button. And I've pulled it out this end as well. Okay. So I've pulled it out everywhere, so if I restart this, and I'm going to make the threshold a little bit higher so the kid doesn't get quite as close. So I've changed the threshold to 450, so the kid doesn't actually get to the point of pressing the button before the buzzer goes off. because I think 250 was a little, you know, he was pretty much on the button based on the light in this room. So again, I'm going to press the button. Going to press the button. And that's what it does. I also did create another version of this, which I'll show you right now. Code challenge. So this is my first version, and then this is a little more of a complicated version. Not much more complicated, but it's you know, there's a little more things going on. So I'm going to get rid of this. So this version, I'm going to go really quick because this one does a lot of the same stuff. But basically, the only difference is I've included this library called pitches.h, so a header file called pitches, which basically is just a bunch of public constants. And you can find this online. But basically, all these defines, which it has a constant for all the notes. So anyone who's musically inclined, all the notes here. And these are the frequencies associated with those notes. So you could make this file up yourself by Googling it and figuring out what the frequencies of each of these notes are. Or if you're not musically inclined like me, you'll just, you know, download pitches.h from GitHub and use it in your file like I have. So I've included that, which basically, again, it just includes pitch definitions for various tones. Basically what frequencies the various tones use. And a lot of the same stuff is happening, but in this case, I've created a Super Mario Brothers theme melody, notes and durations. So I've got this one-dimensional array called Mario Melodies, which is a one-dimensional array of type int, and I've made it constant so that these values can be changed. And it basically has note E7, you know, E7, E7, 0, note E7, 0. Well, these are the notes associated with the Mario theme, and these are like pauses, you know. Well, not pauses, they're zero frequency, so a pause. And then I've got the durations, so a one-dimensional array of type int, again a constant, that has the same number of elements as this one, and this is the durations, how long I want each of these notes to play. So this first element of this array corresponds with this first element of this array, and so forth. And so this last element of this last array is this. So these values are associated with how long I want each of these notes to play. So I won't bore you with the details. Pause the video, look at the code if you want, or I'll upload the code. But basically it does the exact same thing, except it plays a Mario theme when, you know, I go to touch the button. So we'll just look at that right quick. So again, when I go touch the button, and that's pretty much it. So again, if you stuck through it this long, thanks. I'll be back with Circuit 1D, and then that might be the last of the videos because I realize I'm really no good at this. But thanks for sticking with me,